Consumer smart devices are built for short life cycles and easy replacement. Industrial hardware is engineered to operate for 30 years, making the architecture of its connectivity an exercise in long-term asset survival. These environments are physically punishing. Facilities like offshore oil rigs require military-grade hardware capable of withstanding constant heat, vibration, and salt air corrosion for decades at a time. The financial risk profile scales with the machinery. While a consumer device failure costs $50 to replace, a catastrophic industrial breakdown can exceed $50,000 in damaged materials and lost production hours. Most of this foundational layer consists of operational technology, or OT. This is legacy iron, massive electric motors and drive belts built long before the existence of modern cloud computing. Modernizing this multi-million-dollar infrastructure is not a matter of replacement. Instead, Industry 4.0 relies on retrofitting this legacy equipment with modern diagnostic layers. When information technology and operational technology converge, it allows a facility to move away from rigid, scheduled repairs toward a system that detects internal wear before a component fails. The evolution of manufacturing began with the transition to mass production. Early factories organized manual labor around the constant mechanical output of electric motors. The subsequent phase introduced high-speed physical automation. Industrial robots took over repetitive tasks, operating with speed and precision that humans could not match. However, these robotic systems lack internal perception. While they are fast, they are unaware of their own mechanical degradation, continuing to run until a part physically seizes. The current shift involves adding a data-sharing network to these physical processes. This connectivity links localized machines to a centralized analytical engine.
A factory only becomes smart when there is a continuous loop between the physical work of the machinery and the digital analysis of its performance data. To see how this works in practice, we can focus on a single mechanical failure point, the ball bearing on the drive shaft of an industrial saw. Under thousands of hours of continuous load, this bearing is subjected to intense thermal stress and mechanical friction. Wear begins as metal pitting. These microfractures shed tiny steel shards directly into the lubricating grease that surrounds the bearing. These shards act as an abrasive. They gouge the bearing track, which generates more heat and sheds more fragments, accelerating the rate of physical decay. If this cycle continues, the friction overcomes the motor's torque, and the bearing assembly seizes. The sudden stall destroys the titanium workpiece and forces the entire production line into an unscheduled shutdown. Because legacy machinery cannot report this microscopic damage, engineers are forced to operate reactively, waiting for a visible failure before they can intervene. Since replacing every machine is economically impossible, facilities modernize through retrofitting, mounting digital diagnostic tools to existing 30-year-old frames. This is level 1, the sensor layer. Diagnostic nodes attach directly to the exterior. Because these are closed systems, sensors capture data through surface-level phenomena. Nodes monitor specific indicators: acoustic vibrations, casing temperature, and fluid pressure. Wired networking is difficult to maintain on a factory floor. In environments with heavy, moving equipment, physical cables are prone to damage and limit floor flexibility. The system requires ultra-reliable wireless communication, preventing data loss through electromagnetic interference. These sensors transmit data to level 2, edge computing, a localized server directly on the production floor. Uploading raw telemetry from every sensor directly to the cloud would overwhelm the facility's bandwidth. The edge node processes and filters this data locally. By handling the data on site, the system achieves near-zero latency, enabling the factory to trigger a safety shutdown within milliseconds if it detects a critical failure. The edge node serves as a translator, turning raw physical vibrations into a standardized digital format that can be analyzed by information technology systems. At level 3, the data reaches the enterprise cloud. This is where large-scale processing power is used to run predictive algorithms against the telemetry. This chart tracks confidence value. The algorithm monitors vibration data to calculate a component's remaining healthy life. The first metric, overall vibration, tracks macro-level shaking. The second, peak fall, captures high-frequency acoustic spikes from metal shards hitting the bearing. The predictive engine synthesizes both the general machine movement and these microscopic impacts.
The result is a confidence value, a mathematical representation of health, starting at 1.0 and declining as internal components degrade. This line establishes a failure horizon, allowing the system to identify a coming breakdown weeks before it manifests in the physical world. This algorithm creates the link between mechanical friction and a digital countdown. To a human observer, the machine is performing normally. However, the enterprise cloud identifies a distinct change in the telemetry. On the chart, the confidence value line drops out of the green zone and hits the yellow warning threshold. This trigger automatically routes an alert from the cloud back down to the edge node on the factory floor. The system simultaneously pushes a notification to a maintenance engineer's mobile device, specifying the degrading bearing and the high risk of a blade snap. Because they have this foresight, the engineer schedules a repair for the midnight maintenance window, replacing the part before it can fail. By utilizing the prediction, the facility performs a minor repair on its own schedule, avoiding the massive costs of a mid-production mechanical failure. This workflow addresses the core pillars of the smart factory framework defined by Deloitte. The architecture provides visibility into legacy equipment, achieving the pillars of connectivity and transparency. Most importantly, it creates a proactive environment. This ability to anticipate needs is what distinguishes Industry 4.0 from the fixed automation of the previous era. This shift requires bridging a long-standing cultural gap. Historically, information technology teams manage data in isolation, while operational technology teams focused on the physical maintenance of the shop floor. Industrial IoT architecture integrates these two departments. The IT network must interpret the physical reality of the machines, while the OT teams rely on the analytical data to perform their work. The smart factory is ultimately a challenge of integration. By teaching legacy iron to communicate with cloud analytics, manufacturing moves towards a state of continuous self-optimization.